Welcome back to Earth Science Lecture, Earthquakes, Part 2 for Bakersfield College. And previously in Part 1, we discussed what causes earthquakes. We discussed what an earthquake represents. And then we discussed the type of seismic waves that are typically produced from an earthquake with respect to the seismic waves being vibrations. And so in this particular review slide from part 1, we have the P wave, which is a compressional wave and compresses materials in the subsurface and expands the materials. The fastest wave and can travel through both solids and liquids. Then we have the S wave, and the S wave is a shearing type wave, moves about 2/3 the speed of the P wave, which means that it's a little bit slower than the P wave and has a tendency to move particles up and down at right angles as the S wave propagates. And because of the characteristic of the S wave only travels through solids. It does not travel through liquids. Then we have the two surface waves, and the first surface wave is the Love wave, which exhibits a shearing type motion, but it's in a horizontal plane and has a tendency to move materials side to side on the surface. And so here's the side-to-side motion of the L wave. Then you have the other surface wave, which is known as the R wave or Rayleigh wave, which will have a tendency to move particles on the surface up and down. So these are the three or the four types of waves that are typically released during an earthquake. And again, as mentioned in part 1, it's again like being at a horse race. When the earthquake releases the energy, the waves move out all at the same time. So this next slide now is a shot of a seismogram. And as discussed earlier, a seismograph station will pick up the incoming vibrations and then produce a seismogram. And a lot of information can be gleaned again from the seismograph with respect to the magnitude of the earthquake, how close the seismograph station is with respect to the epicenter, and it gives you time spots in terms of the P and the S wave arrival. So looking at the seismogram, typically a seismogram will start off with a little bit of activity right here, which really represents what we call background noise. The earthquake has not reached the seismograph station as of yet. The background noise just lets the person know that the seismograph station is on. So on the onset of an earthquake, and knowing that all the waves are released at the same time, what would be the first vibration or the first seismic wave to come in contact with the seismograph station? And hopefully at this point, folks are saying, well, it's got to be the P wave, because again, the P wave is the fastest of all the waves. And sure enough, if this is background noise, the next tick or tick up or down is going to signify the arrival of the P wave time. So here in the diagram, you can see that the needle starts to move right here, which is now telling you that this is the P wave. So the first major jog will indicate the arrival of the P wave. So the P wave begins to make its way across the moving chart, the seismogram, and you can kind of see that most of the waves that are coming through are somewhat the same, a little bit higher right here, but most of them are kind of tight and the same. And then as it progresses, the next major jog, and in this case, you'll notice that the next major jog is quite bigger than the first initial of the P wave. And this next major jog would be what we regard as the S wave arrival time. And so the P wave comes in first, the S wave comes in next, and basically what we produce is a time interval. In other words, we have a time between the P wave arrival and the S wave arrival. and this is known as the SP interval. And so the SP interval is the S wave time subtracting the P wave time. And this interval is very important because this interval tells the interpreter how close the seismograph station is with respect to the epicenter. In other words, it says that the shorter the SP interval, the closer to the epicenter that the seismograph station is. And conversely, the longer the SP interval time-wise, the farther the seismograph station is from the epicenter. So I suspect if an earthquake took place along the San Andreas Fault and our seismograph station in MS6 picked up the vibrations, I would suspect that it would be a very small SP interval because we are 70 miles from the fault, and we now know that the waves travel pretty fast. And then beyond the S wave arrival now is a mixture of all the waves, the L waves and the R waves and P and S waves. And so most seismologists are concerned just with what the SP interval is telling them. And also seismologists are concerned by the height of the squiggly lines. And so at this point, we are now going to take the term squiggly lines and we're going to convert that to the word amplitude. So each one of these squiggly lines are an indication of how much shaking is taking place. And so again, what we're looking at then are amplitude lines, and the larger the amplitude, the more shaking that is occurring. So for example, if we come up to this particular amplitude right here, this appears to be the largest amplitude in this particular seismogram, which means during this point in time, most of the shaking or people are going to feel most of the shaking right at this time point, which if you look at the bottom of your seismogram, you see a time bar. And this time bar at the bottom is in this case in seconds, and you see 0, 10 seconds, 20, 30, 40 seconds. So we would say that 40 seconds into the earthquake right here, we would say that that is the time of the maximum amplitude or the maximum amount of shaking at this point. And so again, a lot of information can be gleaned just by looking at how the waves come in contact with the seismograph station. So the next few slides, we're going to discuss how earthquakes are measured. And so if you look at the top of the slide, it says, did you feel the earthquake? And really the question is, what's the difference between an 8 magnitude earthquake and a 6.5 magnitude earthquake? And at this point, you're probably saying a 1.5. And that may not mean much to you, but as we progress through this discussion in terms of how you measure earthquakes, when you hear an 8 magnitude earthquake, for example, you should be shaking in your boots with respect to the amount of shaking and energy release. So there's 3 ways to measure an earthquake. And there's the Mercalli's intensity scale, there's the Richter scale, and the moment magnitude scale. The modified Mercalli's intensity scale basically measures the intensity of the earthquake in which how much damage has occurred on the Earth's surface. So logically, the closer you are to the epicenter, the more damage that's going to be observed. And the farther from the epicenter, the less damage is going to be observed. And typically, the way information is gathered is through folks, through people. So after an earthquake, you can kind of envision folks carrying around clipboards, interviewing people, asking people what they saw. People will describe what they see. And then based on that description and observation, the destruction or damage is assigned a Roman numeral. And the Mercalli scale is set up from Roman numeral 1 to Roman numeral 12. And Roman numeral 1 being the least intensity, Roman numeral number 12 being the greatest intensity. So below at the bottom of your screen, you see a Mercalli's intensity map. And this looks like it's somewhere near the northeast part of the United States. I see Iowa, Wisconsin. And this is a map that shows an earthquake that has taken place, and folks have gone out and interviewed other folks. And based on the damage, these areas were assigned various Roman numerals. And you can see that down here is Roman numeral 8, Roman numeral 6, 5, and 4. So you can certainly see that the Roman numerals are progressively getting less away from what we would call the epicenter. So where the higher Roman numeral exists is probably more likely where the epicenter has taken place. This slide here shows the scale of observation correlated with the different Roman numeral numbers. And so this is the modified Mercalli's intensity scale. So for example, if somebody said people, if they observe that people run outdoors, damage to poorly built structures, this would be assigned a Roman numeral 7. Look at Roman numeral 10. Some well-built structures are destroyed. And then at the bottom of your screen, look at Roman numeral number 12. Damage total, waves seen on the ground, objects thrown in the air. So again, the modified Mercalli's intensity scale is based on observed damage. So think about that. If the data taken to produce a Mercalli's map and to assign various damage numbers from the Mercalli scale is based on people, how does that fare with respect to accurately seeking scientific data? And in fact, the major problem with the Mercalli's intensity scale is that it's based on people's opinions, based on people's descriptions. And so what do you know about people and what do you know about their opinions? Well, everybody has one. And it certainly is true that two people can see the same situation but have different opinions and different observation. So along comes Charles Richter in 1935, and he says, we need to produce and make a scale that takes the people out of it. And so he developed the Richter scale, which now measures the intensity of an earthquake that uses the seismogram, as opposed to relying on folks' opinions and so forth. So I think to really get a handle and understand what the Richter scale is all about and what it means is we're going to take this word intensity and we're going to change the word intensity to the amount of shaking. So let me repeat that. We're going to take the word intensity and make it the word amount of shaking. So whenever you hear that word intensity, in your mind you say the amount of shaking. So the Richter scale then measures the intensity of an earthquake using a seismogram. So we're really saying it measures the amount of shaking of an earthquake using the seismogram. And so the maximum intensity is based on the largest amplitude recorded. So if you think back to the couple slides ago, I showed you a picture of the seismogram, and we pointed out the largest squiggly line, which in this case would be the largest amplitude. And so when the Richter scale looks at the amount of shaking or intensity, it's based on the largest amplitude. So earthquake intensity from the Richter scale is based on what we call a logarithmic scale. And the way the logarithmic scale works basically is doubling numbers. So for example, if I go 2, 4, 8, 16, 32, then it becomes 64, and so forth. And so when we look at the steps in the Richter scale, like magnitude 1, magnitude 2, magnitude 3, and so forth, we're going to say that the intensity is going to increase 10 times for every increase step in the Richter scale. So, for example, if we drop down to this bullet point here, and we say that we're going to compare a magnitude 4 earthquake with a magnitude 5 earthquake, we would say that there is a one-step difference, 5 minus 4, one step. So that one step difference indicates that the intensity will be 10 times larger on the M5 than the M4, because we just increase the steps of the Richter scale by 1. If you come down to the next bullet point here, now we're going to compare an M3 magnitude with an M5 magnitude earthquake, and we would say that now we're looking at 2-step difference, meaning 5 minus 3 is 2, and we would say that now, because it's a logarithmic scale, we're going to say 10 times 10, which is 100. So now we're saying that a magnitude 5 is 100 times more intensity than a magnitude 3. So as you can kind of see, every time you increase the step, you're increasing the intensity by 10. And so let's compare, which is not on this PowerPoint slide, let's compare a magnitude 3 with a magnitude 6 earthquake. And the first thing we ask is, what is the magnitude step difference? That would be 6 minus 3. So now it's a 3-step difference. And in this case, we're going to go 10 times 10 times 10, which is now 1,000 times more intense. And so again, as we increase the step, we increase the magnitude by 10. So let's shift gears and come down to the middle portion of the PowerPoint slide. And let's look at, what about the energy that's being released? So in this case, we're going to look at energy in the unit of ergs. And we're going to look at the fact that for every Richter amplitude increase, the energy in ergs is going to increase 32 times. So again, we're looking at energy release. And so we're going to treat the 32 just like we did with the intensity, and we're going to increase it logarithmically. So for example, if we come down here where my arrow is, we would say then an M6 releases 32 more times energy than an M5. Why? Because there's a 1-step difference. I had to drink some water there. If we come down to the next sentence, we'd say an M6 is going to release blank more times than energy than an M4. And so we'll compare the steps from an M4 to an M6. There's 2 steps. In this case, it would be 32 times 32. And we would say that that's 1,024 more times of energy, which is equivalent to 100 times more intensity. How about below that one? We're going to compare an M6 with an M3. We'd say there are 3 Richter steps. And so we would go 32 times 32 times 32. And for the algebra people, 32 to the 3rd power. And that becomes 32,768 more times energy. And finally, we can go down and look at the last bullet point, and we're comparing an M2 with an M6. That's 4 Richter steps. So that would be 32 to the 4th power, and that would be 1,000,000 times more energy. And so really what you should observe here is that every time you increase a step on the Richter scale, it increases 32 more times. And so these numbers are drastically getting higher and bigger quickly. And so when one says a magnitude 8, that should put perspective on exactly how much energy is being released. This slide here is a typical slide that I draw on the board when we're doing a face-to-face lecture. And I hope that this kind of brings it into perspective a little bit on how the energy release works with respect to intensity. So what I have listed here is, for example, I have the Richter magnitudes here. So there's 1, 2, 3, 4, and then we're going to go all the way down to a magnitude 8. And so on the intensity side of the scale, which means the amount of shaking, if we compare a magnitude 2 with a magnitude 1, then that's 1 step. That's going to be 10 times more intensity. If I compare magnitude 3 with a magnitude 1, that's 2 steps, and this is going to be 10 times 10, which is 100 times more intensity. And as we discussed earlier, if I compare a 4 magnitude with a 1 magnitude, 3 steps, that's 10 to the third power. And you can notice that the intensity is increasing by 10. So in this case, it'd be 1,000 more times intensity. And then just to show you how powerful an 8 magnitude earthquake is, we can take a magnitude 8 down here and we can compare it to a magnitude 1, which is a 7-step difference. And so an 8 magnitude earthquake would yield 10 to the 7th power of intensity. And for those familiar with scientific notation, that means that 7 is going to add 7 zeros onto there. And so you should be thinking, wow, that's a lot of intensity or ground shaking for an 8 magnitude. Then if we go to the other side of my diagram, this lists the energy release. And so here, again, we compare 2 to the 1 step, 32 times more energy released. We compare a 3 magnitude with a 1 magnitude, 2 steps, 32 squared, more energy release. A 4 magnitude compared to a 1 magnitude, that's 3 steps, 32 to the third power amount of energy released. And now to really put this in perspective with respect to how much energy is released during an 8 magnitude earthquake, we can come down here and say an 8 magnitude compared to a 1 magnitude is a 7 Richter scale steps. And so if you look at the bottom of your slide, you'll see 32 to the 7th power, which is equal to about 3.4 times 10 to the 10th ergs. And so you should be saying, is that a lot of energy or a little energy? And certainly at this point, that is a lot of energy. So this next slide kind of gives you a statistical look at what we feel annually with respect to various Richter magnitudes. And here you see you have earthquakes that are magnitude 2 or less. Generally, we have about 600,000 of those earthquakes per year, and then 2.0 to 2.9, 300,000. And as the magnitudes increase, we can say, fortunately, the frequency per year gets less and less and less. And finally, we get down to where any kind of earthquake, 8 magnitude or greater, would be about 1 to 2 earthquakes a year. And so that's fortunate for us living on this earth that we don't experience 8 magnitude earthquakes all the time. But it really tells you also that look how dynamic and look how active your earth is with all the numerous earthquakes that take place once a year. And that's, evidenced by plate tectonics in terms of the continents being on the move and shifting around and so forth. So this is a little slide to kind of give perspective of what it means in terms of how much energy is released from an earthquake and what that energy can do. So we can start with this little funny one slide up here where it says magnitude 4.2 earthquake, and I just show a little trash can that's being tipped over. However, if you increase the magnitude by approximately 1 step, now it's enough energy to begin breaking streets and pavement, and I can increase the magnitude 1 more step, and now this person is now cleaning up a mess of wine bottles. But look at this, we go from a 6.6 magnitude to a 7.6 magnitude, and now it's enough energy to start pushing over buildings. And just by increasing the magnitude by 0.2%, now neighborhoods are being destroyed. And then, of course, here's an 8 magnitude earthquake here. And, of course, this complete and massive devastation. So really what you should glean from this slide is that the energy, again, is growing logarithmically. And just because you increase from 1 step on the Richter scale to the next step on the Richter scale isn't consecutive, but more logarithmically. And so that translates into much, much more energy release and much more damage. Well, we've looked at the Mercalli's scale. We've looked at the Richter scale. Let's now take a look at the moment magnitude scale. And the moment magnitude scale is sometimes symbolized as MMS or M with a subscript W. And the moment magnitude scale is the current seismic scale that is used today. And it's based on physics. It's based on the work done, which I believe when we say work done in physics, we're talking about um, I believe it's mass. Well, I can't remember. Mass times distance, force times distance. And so it's based on the work of force times distance. But really, what the moment magnitude scale does is it measures the energy released of the earthquake based on what we call the moment of the earthquake. And when we say moment of the earthquake, let me be clear that moment doesn't mean a time unit. Instead, moment means a variable in the work done for the work done for moment magnitude scale. So if we come down to the moment, we're saying that the moment is going to be equal to the rigidity of the Earth, which incorporates the rock properties that the seismic waves travel through, times the average amount of slip and size of the area. And really, what's going on with the moment magnitude scale is the moment magnitude scale is a better way to acquire data. So it's much more accurate, for example, than the Richter scale. Because when we look at the moment and we look at the rigidity of the Earth rock properties, that's more of a realistic approach, because when an earthquake takes place, the seismic waves travel through different types of rock material. And we know that when seismic waves travel through various types of rocks, the velocities and the direction of the waves are going to be changed. And so the moment magnitude scale accurately takes in this data as opposed to what the Richter scale does. So the moment magnitude scale, again, is used today. It was developed in the 1970s and again replaces the Richter scale. But it only replaces the Richter scale, again, in terms of how it collects data. Because if you look down here towards the bottom of your slide, the moment magnitude scale still uses the same values defined by the Richter scale. So in other words, as you increase the magnitude steps, it's still going to, the intensity is still going to increase by 10 times, and it still uses 32 as the amount of energy released. The moment magnitude scale is currently used by the USGS folks, United States Geological Survey. Well, what's going to happen for exam purposes for earthquakes is you're more than likely are going to see an essay question that's going to ask you to define the differences between the Richter scale and the moment magnitude scale. And so I've tried to present a bullet pointed slide that kind of gives and highlights the characteristics of the Richter scale and compares that to the moment magnitude scale. So if you look in the orange print of your slide, I have some bullet points describing the Richter scale. And if we look at those, the Richter scale assumes the earthquake focus is a point. So this represents, when you look at the focus in the subsurface, that as the rupture takes place, it's a single point. The Richter scale is best suited for earthquake energy released from a small area. And reason for that is because if it's a smaller area, then the seismic waves don't travel through different kinds of rock material. However, the reality is that during an earthquake and release of seismic waves, it certainly expands over broader areas. And then when you look at the Richter scale, it's based on the intensity. Okay, you know what that means. The amount of shaking is based on the amplitude measurements. In other words, all the Richter scale cares about is shaking. And all it cares about is that needle moving back and forth on the seismogram and measuring the amount of shaking or the intensity. And if you compare that to the moment magnitude scale, the moment magnitude scale assumes energy is released over a large area, which is much more realistic during an earthquake than smaller areas. And then the second bullet point, which is probably the most important, is that the moment magnitude scale considers rock types that the wave travels through. In other words, the seismic waves, again, will travel through igneous rocks a little bit faster, for example, than they would sedimentary rocks. So again, data produced from the moment magnitude scale is much more accurate than data produced from the Richter scale.